Alrighty, let's get started. Hi everyone. Um, Glad to be back. Hope the remote lecture wasn't terrible. And then kind of learned what they need to learn. But we'll recap what we did last time. Um, this is a robot snake from CMU. It's a real thing. It kind of looks like the snake from Dune, so I thought that was cool. But look it up. There's a professor how he chose it, who does lots of cool work in this area. So um, yeah, that's a good place to start. So let's start with our quiz. What form did the motion models in Kalman filters take? The options are quadratic polynomial, logarithmic, linear Gaussian, Poisson, none of the above. Give it me 20 seconds. Right, last 5 seconds. Cool. All right. So the answer here is linear Gaussian, and we're gonna recap that in a second. Um, some logistics to start. We're gonna have our first seeded paper discussion this Friday. I sent a email out to all the teams who are presenting. There'll be 3 teams presenting. So the way it's going to work is we assign 2 papers. Teams that are presenting, pick one of the papers, build on it, and teach us something new. Give us a new idea. The cool thing is you don't have to actually do it, so you can just make up stuff. But like you have to defend it to the class, right? So tell us why it matters. Tell us what the technical details are. Tell us what experiments would validate your claims, right? Um, and the rest of the class who's not presenting, read the paper so that um, you're not like struggling to keep up with the new ideas, right? And so um, that's the first piece of logistics. Second is homework 2 should be due next week. So yeah, get started on that if you haven't already. Cool. So let's do a little recap. We started by talking about Bayesian filtering. We talked about going to belief power. Belief power with the particle filter was basically pushing things forward through our motion model. So we didn't need anything like Gaussian assumptions. We didn't need linearity. We just pushed things forward to the particle filter. Then we had a measurement update. The measurement update was basically reweighting particles by the normalized measurement likelihood. So P of Z given X, right? So we reweighted particles and then we did things like resampling, right? And so what the particle filter was basically a mix of pushing things forward and reweighting and resampling. That's it, right? And then from there we said, okay, we did this thing, but it's an approximation, right? So how can we be tractable in closed form, right? So how do we find something where these intervals are easy to evaluate, not just like a pain? And so we said, okay, what if we model things as a linear Gaussian, right? So when we said linear Gaussian, that means that the mean of your Gaussian, oh, sorry. Um, the mean of your Gaussian is going to be some linear function of um, xt minus 1 and ut. And the measurement is going to be some linear function of xt, right? So the mean is going to be some linear function of xt. So when you're saying things are linear Gaussian, that means that like the mean is linear, and the probability distribution is a Gaussian, right? And so that's going to make things easy to evaluate, right? Okay, so whenever you think of a Kalman filter, think of a Kalman filter as a Bayesian filter, something that just implements these 2 things, but it has the motion model as linear and Gaussian, it has the measurement model as linear and Gaussian. Okay? It's a special case where you can solve these exactly. Okay, and then what are Gaussians? So we talked about univariate Gaussians and multivariate Gaussians. We'll generally think about things multivariate because it's more general. Um, but a multivariate Gaussian can be thought of as, univariate Gaussian is kind of like a bell curve where the highest point is the mean and the variance determines the width, right? A multivariate Gaussian can be thought of as like an ellipse, right? So the mean is determined, the center of that ellipse is determined by the mean, and then the width and direction of the ellipse are determined by the covariance matrix, right? So More the covariance, the wider the matrix. Smaller the covariance, the more narrow, or more higher the covariance, the wider the ellipse. Smaller the covariance, that like sharper, right? And if you have no off-diagonal elements, then this is going to be axis aligned. And if you have off-diagonal elements, you can see that it like kind of rotates. And so Gaussians are very nice to visualize geometry. Okay, and so whenever you think of a Gaussian likelihood, it looks something like this. And the nice part about Gaussian likelihoods is because they're exponentials and exponentials integrate to themselves, you can often get like nice closed form solutions for Gaussians. Yeah. So the reason Kalman filters are easy to evaluate is because exponentials, when you integrate them, exponentials just have nice properties. When you integrate them, when you multiply them, they just tend to be more compatible with integration. Okay, so some identities, which we're not going to actually work out in detail. If you all want to see the things worked out in painstaking detail, just look up my CSE 571 class. I spend like hours on it. But it's kind of a pain, right? So, but let's just take these identities for now and try to work with them, right? So the first identity says that if you have x, which is a Gaussian, some random variable x, which is a Gaussian, and you have y, which is a linear function of x plus some Gaussian noise, right? So it's like x is a Gaussian, y is like a linear function of x plus some extra noise, epsilon, which is also Gaussian, right? Gaussian, which is zero centered with the variance q, right? So it's like x is your original random variable, y is something that moves this thing by ax plus b, and then add some extra noise to it, right? If you have this, then you can show that y is also a Gaussian. It's a Gaussian with mean a mu plus b and variance a sigma a transpose plus q. Right? So let's try and make sure we understand the intuition here. The intuition here is that let's say your ellipse for x was like this, right? And then y is like a linear function of x. So it's kind of like you move things linearly to another spot. And then you're going to add some extra noise to it, right? So the mean is just going to be shifted by a mu plus b. It's like you take the mean and shift it linearly. And then the variance, there's two terms to it. The first term is just saying if you have a random variable x, you scale that random variable x by a, the variance is going to become a squared variance x. So if you look at the variance of ax, it's generally the a squared variance x. And so if you look at the definition of variance, you can derive this. But whenever you have variance of a random variable, you scale it by a scalar, the variance is scaled by the squared, right? And so in some sense, the first term is just like the variance scaled by a squared, and it's just in matrix form. So your original variance was sigma. You scaled your random variable by a, right? You have ax, which means that the variance is now scaled by a squared. This is just the matrix form of a squared. Yeah. And then you're going to add noise of epsilon, which is centered at 0 and has extra variance q, which means that your Gaussian is now going to be a little bit wider because you added a little bit more noise, right? And so the way you can kind of think of this is this shifts the mean, this scales the variance, and this adds the extra variance from this extra noise, right? And so the foreshadow here is basically that this is kind of going to be like your motion model, right? And this identity is going to help you figure out the predictions in your Kalman filter, right? Make sense? Intuitively, you can kind of think of it as this ellipse moves somewhere else and then becomes a little bit wider because of the extra noise that you had. Plus, like some scaling terms because of A. Any questions? Okay, so that part makes sense. So that's our first identity. Our second identity is a little bit more confusing. But our second identity is saying, okay, now you've like shifted your Gaussian somewhere else, right? So you have your x coming from with a Gaussian of mu and sigma. You have a y, which is a linear function of x again, again with some extra noise because your sensors will be noisy. You can kind of think of this as your motion model. You can kind of think of this as your measurement model. We'll make it precise in a few slides. But intuitively, what it says is that if I want to refine my distribution over X, when I get extra evidence that Y is equal to Y naught, how do I do it, right? So the question is, I have this Gaussian. This was my uncertainty over what X was going to be, right? And then I got some evidence, not about X, but about some related thing Y, right? So Y is a related thing to X. Y is related to X through this linear relationship. And so extra information about what Y is will give me some information about what X is, right? And so I can narrow my distribution of X with this extra piece of evidence. Kind of makes sense? So you can kind of think of this as like, this is saying that like, oh, sorry. You can kind of think of this as saying that, hey, this is my initial Gaussian. There's like some transformation from here to Y, right? Now, someone gives me evidence that Y is exactly equal to Y naught. I like take this back and now I refine this to be like a smaller Gaussian, right? So I can shift the mean, shift the covariance according to the evidence that I got that like some related variable Y was equal to Y naught. Right? I'm going to shift this all the way back to refine my distribution of X, right? So you can derive this if you want by like just solving the conditioning. Like you can write this as P of X divided by P of Y equal to Y naught. You can kind of solve this if you want with integrals and everything. You'll get the right answer. But intuitively, let's think about this a little more. Intuitively, you can kind of think of this as saying, take your original mean and kind of move it towards like the thing that would happen, like move it in between your original mean and like what Y naught would suggest, right? So it's saying that like if you're at if your X was at mu, then your Y would be at C mu, right? Because it's linear. So if your X is at mu, your actually there's no B here. But if your X is at mu, then your Y is at C mu, right? And so you look at the difference between C mu and the actual Y naught that you got, and you use that to move your mean. And so the first step is kind of saying like, you look at the difference between the mean and what you actually got and use that to adjust the mean of your Gaussian. And the second one is saying that like you look at this extra piece of evidence and you kind of shrink. You can kind of think of this as shrinking your uncertainty. Right? So this I minus KC is kind of shrinking your uncertainty. So this is like you can kind of think of this as interpolating. It's interpolating between your previous belief and an updated belief, and this is kind of shrinking your uncertainty. Go ahead. I haven't defined it yet. It's like it's a little nasty. But we'll define. It's a function of C and sigma and R. It's like sigma C transpose by sigma C sigma plus R, something like that. Um, we'll get into the details of it, but it's basically you can kind of think of it as it's how much should you it's something that tells you how much should you trust Y as a measure of X. So it's like if K is small, that means you really shouldn't trust Y as a measure of X. If K is large, that means you should completely trust Y as a measure of X. Um, okay, so we'll get into the details of that, but for now, let's just think of this as a constant, which is a function of this and this and this, right? So you can think of this as like correcting the mean between what you thought it was and what the evidence suggests, and you can think of this as shrinking your confidence, right? So or shrinking your uncertainty. It's like saying that you become more confident with more evidence. Okay, everyone kind of with me on this intuitively, right? This is saying move the mean, expand the variance. This is saying adjust the mean, shrink the variance. And then kind of parses with what we saw with particle filtering too, is that the motion model kind of increases uncertainty and the measurement model kind of shrinks uncertainty. But we'll connect it more exactly in a few slides. Okay, so the key point of linear Gaussian things is that it once a Gaussian, always a Gaussian, right? So If you do marginalization and conditioning in Gaussians, that gives you more Gaussian. And so as long as we stay here and we do linear things, we'll continue to be Gaussian, and then things are nice and easy to evaluate. So that's a recap of Gaussian identities. Any questions? Does that make sense? So now what we're going to do is take these identities. We're going to try and derive a Kalman filter from these identities. So like get an exact expression for what the dynamics update and the measurement update are going to be. Okay, let's keep going. So what is a Kalman filter? A Kalman filter is just a Bayesian filter, which has linear Gaussian dynamics and linear Gaussian sensor models, right? So the scalar version of a Kalman filter is going to look something like this. It's going to say that xt is going to be equal to axt minus 1 plus but plus epsilon t, where epsilon t is a Gaussian sampled from 0 with variance q, right? So you can kind of think of this as like it's like a linear equation that's telling you how to go from one time step to the next, but you're adding a bit of noise to it, yeah? Bit of uncertainty. And then your measurement model is somewhat related. It's saying that your measurement model is some function c or some linear coefficient c times xt plus delta, where delta is again a zero-centered Gaussian with variance r, right? And so Kalman filter is just completely defined by these coefficients a, b, q, c, and r. Yeah.
Maybe it was directly related to, but when we were talking about noise like those sensors, it had that really silly looking.
Yep.
The same.
It's not. It's not Gaussian. Like we had this, you're talking about like this thingy, right?
Yeah, is that the equivalent of?
This one?
Yeah.
So it's saying that delta is actually a Gaussian and not this thing. So this thing was the combination of 4 different things.
But that's like trying to add noise to our measure. Where this is also trying to add noise.
Yeah, but they're just from different distributions. So like that's why we use particle filters in your homework, because they make the least assumptions. And they trade off tractability with computations. Particle filters will work with any noise distribution, whereas Kalman filters only work with Gaussian noise distributions. And so we'll talk about how to extend this to nonlinear things, but it's really hard to be non-Gaussian. Okay. Questions? Does it make sense? As a framework, we're just saying dynamics are linear, measurements are linear. You just add some noise. The noise has to be Gaussian, zero-centered Gaussian, right? And if it's not zero-centered, you can always, it's just like shifted by a constant. You can always absorb that into the linear function. It's like you can, as long as it's Gaussian, you're good, right? So all that a Kalman filter is linear dynamics, linear measurement. You can kind of go from there to the matrix version of this, which is what's commonly used, which is saying that xt is equal to axt minus 1 plus but, where these are matrices. All right, so if this is, let's say, m by 1, right, this is m by 1. Let's say your action was n by 1. Right, this matrix is going to be what size? M by m. And this matrix is going to be what size? M by n, right? And then this epsilon you're going to sample is again a vector. It's going to be an m by 1 vector, right? And similarly, your noise will be sampled from mean 0, covariance q. Covariance q is again going to be an m by m matrix, right? And so whenever you want to think of these matrix dimensions, just like try to make sure you pattern match with this thing. Similarly, with your measurement, let's say your measurement was of size k by 1. Your state was m by 1, so your c is going to be k by m, right? And your delta is going to be k by 1. And this is going to be something of size k by k, right? So just matrix. It's the matrix version of your scalar. Okay, so this is the version we're going to use in our Kalman filtering. Generally, like a Kalman filter is fully determined by A, B, Q, C, and R. Right? And they kind of tend to use these letters. A and B denote dynamics, C denotes measurement, Q and R denote noise. Okay, everyone with me on the definition of the Kalman filter? Okay, so if you ever want to look back at these, I kind of have a cheat sheet. They're on the slides. But the goal of the Kalman filter is kind of the same as the Bayes filter, right? You have a belief that you're trying to estimate. Xt given u 0 to t or u1 to t and z 1 to t, right? You're trying to do a recursive update. So you're trying to do a recursive update where you have a measurement model, a motion model, and you're trying to propagate things recursively. So you're going to do a dynamics update, which is going to go from belief to belief bar. So it's going to go from belief at xt minus 1 to belief bar at xt. And the measurement update is going to go from belief bar to belief. Right? So we're just going to try, now with all our Gaussian magic, we're just going to try and revisit these two steps, plug in our identities, and get, magic, easy to implement stuff. Yes? Good. Alrighty. So let's start by trying to instantiate these different steps, right? So if you remember, we have our prediction step, our correction step. Let's start by thinking about our initialization. We're going to have our initialization be just a Gaussian, right? So you don't know where you are exactly. You're going to have some mean mu naught, some variance sigma naught. It could be a really large variance, and you're going to refine it with measurements. And so you're going to say the notation I'm going to use is a little bit weird. It's going to be that your belief at any step is mu t0 to t. So the thing on the left of the bar is the thing that you're trying to measure, or the thing that you're trying to model, and 0 to t is the evidence, right? And so I'm going to say that like whenever you have mu t0 to t, that means you're trying to figure out the distribution of mu at time step t, or trying to figure out mu at time step t with evidence from 0 to t, right? You're going to figure out variance at time step t with evidence from 0 to t. Right? And you're going to like have belief bar be the one without incorporating the measurement at the last step. Okay, so let's start by thinking about our prediction model, right? So generally, I don't really, we're not going to use this in our homework. It doesn't matter if you don't get it exactly, just get the general gist because it's useful. So you're going to have your measurement model, or you're going to have your dynamics model. It's going to go from xt and ut plus 1 to xt plus 1, right? And what you're trying to work out is how do we incorporate just one action without incorporating the next measurement, right? And so if you look at the thing we're trying to work out, we're trying to go from belief to belief bar by solving this integral. Right? And so we're not going to work through the integral, but what we're going to do is we're going to do a little pattern matching to our previous identities. Right? So if we do a little pattern matching to our previous identities, our identity says that if x is from a Gaussian and y is a linear function of that Gaussian plus epsilon, where epsilon is again a Gaussian, then the distribution of y is this thing, right? So, okay, can someone tell me so now we know belief, we're trying to get a belief bar. So what is belief bar going to be? So remember that belief was a Gaussian. Let's say belief was a Gaussian, mu t 0 to t, sigma t 0 to t. Right? So this was belief at xt. Now we need to get to belief bar at xt plus 1. So how do we get there? We're just trying to pattern match, right? So we're trying to say if y is a linear function of x is Gaussian, then we know how to get to y. We've defined xt plus 1 as a linear function of xt and some other stuff. we've said the distribution of xt was that thing, belief of xt. How do we get to belief bar of xt plus 1? And you can't look at the next slide. But don't go to the next slide. Just tell me what do you think it's going to be, and walk us through it.
You mean like,
Please go.
no, just, you, and then. Given,
But tell me mu t plus 1 in terms of mu t and a and b and q.
Oh, okay, okay. I'll have to think of it.
Okay, yeah, think about it. Take your time. All we're trying to do is pattern match, right? Like, let's try to just pattern match what is x, what is y, what is b, what is a, what is q. And like, it should kind of fall out of this identity. Okay, so remember, we're trying to go from let's just go step by step, right? What is x? We're trying to go from belief to belief bar the next step, right? So what is our random variable x going to be in this case? Belief at xt, right? So like x is going to be your belief at xt, right? So the belief at xt, which means that mu here is just going to be mu t 0 to t. Sigma is just going to be sigma t 0 to t. So it's just your belief at your current step, right? So x is just your belief at your current step. The next thing we have to figure out is what is y, right? So what is y? xt plus 1, right? So y is going to be xt plus 1. And a here is actually just a here. B here is what? Yeah, yeah, yeah. It's just BUT plus 1, right? So B here is just BUT plus 1. And an epsilon here is just epsilon t plus 1, right? So if we just, let me see if I can erase these things. So all that x is just the belief at xt. Y is just the belief bar at xt plus 1, right? And a is a, b is but plus 1, epsilon is epsilon t plus 1, right? So it's like you can literally use this identity. There's nothing there's nothing fancy here. You're just doing some pattern matching, right? And so if we were to and we're going to say that belief at time step xt was a Gaussian with mean mu t 0 to t and variance sigma t 0 to t, right? So now, given this identity, what is belief bar in terms of mu, sigma, a, b, and epsilon, or a, b, and q, sorry. Right, so we're just trying to substitute this pattern matching that we did to give us belief bar. Yeah, so just walk me through it. It's going to be a Gaussian. BUT plus 1. Perfect. And what's the variance going to be?
Oh, okay.
Perfect. That's it. That's it. Yeah. Maybe the question is too obvious. But yeah, I just wanted to make sure we're just like systematically doing pattern matching. So that got it exactly right. We're basically just saying probably have this typeset on the next slide. So we're just saying if your previous belief was a Gaussian with mean mu t0 to t and variance sigma t0 to t, your belief power is just going to be a linear function of these vectors. It's going to be linear a mu plus b u, and the variance is going to be quadratically scaled plus you add, right? Plus you add, right? So it's exactly matching. It's exactly using the identity. But whenever you want to use these identities, you just want to pattern match one variable to another. Oh. So you look at this guy, look at this guy, you just try to pattern match, right? So xt plus 1 is y, xt is x, and so on. Yes, everyone with me? So all that we need in the Kalman filter, all that you do in the prediction step, you just need to do, you don't need to do anything. You don't have to like sample, push things forward through the motion model, nothing like that. You just take your previous mean, multiply it by a matrix, and add it. You just have to do matrix multiply. It's just linear, nothing else. Right? So the nice part about a Kalman filter is it's super efficient because just matrix multiply. You don't have to iterate through the particles and push them forward and reweight them. You don't have to do any of that. Okay, so yes.
What area each step, like sigma, sigma value I use. Are any variables like
So you can kind of think of it as you started with some mu and sigma, right? And then let's say at the next step, let's call these mu naught sigma naught. These are just constants you start with. And if you want to compute mu1, right, you're just going to say mu1 is equal to a mu naught plus bu 1. That's it. And then you're going to say sigma naught, or sigma 1 is equal to a sigma naught a transpose plus q1, right?
a
So A and B don't change. A and B are part of your system. Q is part of your system. Like the mu's are connected to each other, right? So you like can compute mu t from mu t minus 1 and mu t plus 1 from mu t, right? But the relationship is always consistent, right? So like, for instance, you went from mu 0, sigma 0 to mu 1, sigma 1 using this linear relationship. Now you could go from mu 1, sigma 1 to mu 2, sigma 2, right? And so the mu's and sigmas are changing just through a linear connection. Oh, because you can have time varying noise if you want. So you can have like a system which has lots of noise at the start and different noise later on. So it doesn't have to be the same noise at every step. It could be like this includes a scenario where the noise is the same at every step. Okay, so we'll get through some intuition in a second. But in terms of like mechanistically implementing a Kalman filter, you just start from mu naught sigma naught, then you compute mu1 sigma 1 just using matrix multiply. And then you can compute mu2 sigma 2 just using matrix multiply. And you don't have to do any like fancy computation. It's just stick in the current mu, the current u, the current sigma into this thing, you get the next mu, the next sigma. That's it. Everyone kind of with me? Makes sense? Let's kind of get some intuition on what we're doing on that. Okay, let's kind of get some intuition on what the Kalman filter means. So one way of thinking about this is that if you have like, let's think of this as your initial Gaussian, right? What this linear operation means is that you're kind of like a linear operation, you can think of it as an affine transformation. That's you're like shifting it in the plane, right? And so you've shifted the Gaussian. Oh no, you can't see my, okay, well, apparently I only have white. I only have black as a marker, so you can't see it, but you have this Gaussian, which is like right here, right? And you're like shifting it according to an affine transformation, a linear transformation. And then you are like scaling the variance, you're expanding the variance, right? So basically, one way of thinking about it is like if A is really large, right, then the variance is going to increase a lot. But if A is really small, the variance is going to decrease. And then you're adding some Q because of the extra noise that you're getting, right? And so you can kind of think of it as you took your initial Gaussian, you shifted the mean and the variance, you scale, and then you add a bit more noise. Right? So you can think of the correction step super geometrically. Shift and expand. Yeah. Cool. I can also there's a nice blog which I got these things from. I'm happy to share that afterwards. Cool. So all that the prediction step is saying is that imagine this was your belief. After a dynamic step, you're going to shift your mean by some amount. This was your previous distribution. You're going to shift your mean by some amount, and you're going to like increase the variance in most cases. Yeah. Yeah. Right. So it's a bit of a problem. And so there's techniques like UKFs and EKFs which will help us deal with that. We probably won't get to it today, but we'll cover it on Wednesday. Okay. Good question. So we're assuming linearity. Yes. Yes. Blue. Okay, so I'm colorblind, so I don't know what the I don't know what the right color names are. But this one is your current belief, and the green was like your um was your measurement at the previous step, and the red was the belief at the previous step. And so for this plot, all you really need to care about is this, whatever. I think this is blue. Um, and then is this purple? Pink? Whatever. Like that is your belief bar at your next step, right? So only you don't worry about the green and red lines here. You just need to care about the blue as your previous belief, and the pink purple thing as your belief bar at the next step. Right. So you can kind of think of it as that, like the main things to think about is that the mean has shifted and the variance has kind of expanded. Right. This is not always true. If the eigenvector or the eigenvalues of A are greater than 1, then it expands. If it's less than 1, then it shrinks. Right? It's kind of like if A is less than 1, you can kind of think of it as like if it's a scalar and A is greater than 1, then it expands. If A is less than 1, then it shrinks. Yeah. Possibilities of the future states. As in, okay, so there's two reasons the variance is changing. One is because of the Q and one is because of the A, right? And so the A is kind of telling you like it's telling you how much your state is getting scaled. And the Q is just additional noise. So the A is kind of referring to your future states, but the Q is more just like inaccuracies in your model. So it doesn't really care about future states. Okay. That makes sense for the prediction model. Should we move on? Pretty happy with it? Good. All right. So the measurement model is harder to intuit, but we'll try to get there. So in the measurement model, again, your measurement is linear. So zt plus 1 is a linear function of xt plus 1 plus delta t plus 1, where delta t plus 1 is again Gaussian noise, right? And you can kind of think of this as just a linear Gaussian with mean cxt plus 1 and variance rt plus 1, right? So what we're going to try and do is we're going to try and figure out how to go from belief bar at xt plus 1 to belief at xt plus 1 using the measurement model. Same thing we did for the particle filter, but we're going to do it for Gaussians. Okay. So we're gonna deal with the reason it's going to be tractable is because Gaussians are easy to normalize. And so we're going to use our identity from before, and I'll kind of define what K is a little more clearly now. But we're going to try and define our identity from before, which says that if you have X, which is a Gaussian, and you have Y, which is, there's a little bit of a typo here. This B shouldn't be there. Ignore that. X, which is a Gaussian, Y, which is a linear function of X, plus some noise. And the noise is again a zero-centered Gaussian. Then the conditioning variable does this interpolation plus shrinking of uncertainty, right? Everyone remember that? We did this a few slides ago. Okay. And for now, let's think of K as a constant, which is a function of sigma, which is the variance of X. Sorry. Hmm. Um, okay, so we can think of this as, well, my pencil has been kind of weird. Hmm. Okay. Pencil's not working, but we'll keep going. So we can kind of think of this as a function of your variance of X, which is sigma, C, which is the scaling variable between X and Y, and R, which is the noise that you add additionally from that delta variable. Right? It's a function of those things. And so let's do our pattern matching first, and we'll try to get some intuition again. Right, so from a pattern matching perspective, what is X? What is X going to be here? So X would kind of correspond to like belief bar xt plus 1. Right, so we're trying to think of this as your X belief bar, and your Y is or actually you can kind of think of X as your state, Y is your measurement, right? And what you're trying to get to is what is the likelihood of your state given an additional measurement, right? So X is going to be the random variable for your current state, given all the previous measurements, not the current measurement, right? Y is going to be your current measurement. And what you're going to try and figure out is what is the likelihood of your current state. What is the likelihood of your current state given previous measurements and the current measurement, right? So you're trying to incorporate the latest measurement. So the way you're going to pattern match this is that X is going to be kind of like xt plus 1 given the previous measurements and actions. Y is going to be your latest measurement, which is going to be zt plus 1. Right? You're going to try and figure out what is the likelihood of xt plus 1 given all the previous measurements, all the previous actions, and then the current measurement. Okay. So really would help to have my pencil now. Mind if I rejoin? And okay, give me 1 second. Let's see. There we go. Okay, so we're trying to figure out what is the likelihood of the current state xt plus 1 given u 0 to t plus 1, given z 0 to t, and the latest measurement zt plus 1, right? So you can kind of think of y as z. You can kind of think of x as x when you're doing the pattern matching, right? And there's no b here, but delta is the same as delta. Yes? Okay, so given that pattern matching, let's go to the next slide. You can kind of use the identity directly, right? So the identity would say this likelihood is going to be an interpolation plus a shrinking. So in our case, if we're going to say that the previous belief, without incorporating the latest measurement, is going to be a Gaussian, this is going to be the result of our prediction step. Like the previous thing we did, right? It's going to give us a Gaussian, right? If you remember, it gave us this Gaussian, which is A mu plus BU and A sigma A transpose plus Q, right? So this thing is this thing is this thing. Yeah. And so what we're going to get next is that our updated belief after taking the latest measurement is going to be previous mean plus k times the difference between the actually obtained measurement and C mu, right? So you can kind of think of this that if your state was actually mu, if your state was actually the mean, this is what the measurement you would have gotten was, right? So C mu is telling me that if my state was truly the mean, then I would have gotten the measurement C mu, right? And so I'm trying to say the difference between what I got and what I expected to get, right? So you can think of ZT plus 1 as the actual measurement that you got. You can think of C mu as what I expected to get, right? And you say, okay, I have some difference between what I got and what I expected to get. And then I like use that to change my mean, right? So I had a previous mean. What I got didn't exactly match what I expected to get. And so I kind of like interpolate between what I got and what I expected to get using um, using uh, using that k to kind of modulate, right? So you can kind of think of this as this is literally an interpolation, which is saying it's 1 minus kc times mu plus k times z, right? So you can kind of think of it as interpolating between mu and kz, right? So it's like saying that you're trying to use the difference between what you got, what you expected to get to adjust the mean. Right? So that's the first step. And then the second step is saying that I'm going to like take my previous variance and I'm going to shrink it by a factor of I minus kc, right? So if one way of thinking about this is if k is 0, right, then the mean doesn't change, the variance doesn't change, right? If k is 1, then the mean shifts completely and the variance goes to 0 and everything else is in between, right? And so it kind of this tells you to correct your mean according to the difference between what you got, what you expected to get, and this tells you to shrink your variance according to your k, which we'll talk about in a second. Okay, so this kind of makes sense besides the k. Good one.
They were, uh, the measurement that kind of reweigh particles.
Yeah.
Whereas the Kalman filter, uh,
It's close one. Yeah.
and we don't necessarily need that.
That's right. You don't need the resampling and stuff because I guess the resampling stuff is just an approximation to make it tractable. Here we're just saying it's going to be exact and close one. If it's linear and if it's Gaussian. Good, Andy. So this is going to be like these are all PSE. So you assume that like there is a PSE. That's going to be like quadratic plus a PSE thing. Covariance is always PSE. PSE is positive semi-definite. Okay, so the main thing you want to understand here is that you adjust the mean by looking at the difference between what you got, what you expected to get, you shrink your variance. And you can kind of think of your K as a measure of how much should you trust your sensor. So your sensor is something that is coming from Cx plus R or Cx plus delta. And if K is close to 1, that means you should really trust your sensor. If K is close to 0, that means you shouldn't trust your sensor at all. We'll go over some more intuition and the nonlinear stuff next time. Thanks.